Here is my Ben Eater SAP-1 computer. I recently completed this and I wanted to continue to build on it, make it do some interesting things. The first goal I wanted to do is make it calculate the factorial. However, Ben Eater's original design would not allow for the factorial to be calculated for various reasons. But I have figured it out. In fact, I'll show you right here. I have 4 in memory address 15, and it calculates the factorial of 4 to be 24. There you go. I have updated this computer to be able to calculate the factorial. In this video, I'll go into how I did this and help you accomplish the same if you're so interested. Some of you might be wondering, why calculate the factorial on the SAP-1? Well, I built this computer to basically learn how computers work. In my professional life, I do software. I develop software. So I have a high-level understanding of how the underlying hardware works, but I wouldn't say I have a detailed understanding. And so I started following Ben Eater's original video series on how to build the breadboard computer with the specific goal of learning. And after I completed the series and completed my breadboard computer, I wanted to prove myself that I actually learned something, as opposed to just simply follow the instructions of Ben Eater's videos. To do that, I wanted to solve a challenge, to make it implement an algorithm that, as originally designed, it couldn't implement in the first place. So I drew from my professional life to figure out what algorithm I would want to use. Now, in my professional life, I am in a position to frequently interview prospective software engineers. And one of the things you learn after doing that for a while is that interviewing someone with a complicated algorithm is not a good way to interview. Instead, I use a fairly straightforward algorithm, but dig in deep and try to see if the person really understands what's going on with that algorithm and what's happening underneath in the language and in the computer itself in order to accomplish the goal of what that algorithm is trying to accomplish. One of the algorithms I use in my interviews is Factorial. It's a fairly straightforward algorithm, and it allows me to ask very deep questions about the basics of computer science and the basics of computer operating. If I use the factorial problem to test prospective software engineers, I figure it would be a good test to see if I really understand how the SAP-1 is designed, how the various components interact with each other in order to accomplish a greater goal. Okay, first let's go over what the factorial algorithm is. Here you have it on the screen. Basically, the factorial is, for any value or integer n, is the value n times n minus 1 times n minus 2, that sequence repeated all the way down to the values of 2 times 1. For small numbers, it's pretty easy to calculate. Like you can see in your head, the factorial of 3 is the value of 6. The factorial of 4 is 24, and so on. For larger numbers, this number gets large very quick. But this algorithm, this actual function, is useful in many different kind of statistical analyses, and so that's where it's used. Now, here you have it implemented, that same algorithm implemented in Python. Python's a fairly straightforward language, and it's fairly easy to interpret it, even if you don't know the language itself. So to implement it here, you have a loop, which requires that you have a counter that you decrement from n all the way down to 1, have the ability to compare that value, and then inside of that loop, you're multiplying that counter that you're using that loop times the results to accumulate what ultimately becomes the factorial value. Now, you may say, hey, I can't actually calculate this value on the SAP-1 because it doesn't have a multiplication function. And so, yes, there is a version of this algorithm. You can implement it without multiplication. And here it is. As you can see, what I've replaced the multiplication with is, instead of just a straight up multiplication, you get another loop. Because as you know, multiplication is really just a series of additions a certain number of times. And in fact, we have implemented multiplication on the SAP-1 as a demonstration program to kind of prove that it works. And so, to implement factorial on the SAP-1, you would implement basically 2 loops, as you see right now, to accumulate values. And here is how you would implement it in Ben Eater's original instruction set. One of the first problems you're going to see is that this is larger than 16 bytes. And so I can't implement it on the stock SAP-1. Like as you built it in the original video series, you just can't implement it because you don't have enough RAM. So how would you implement the factorial? I got to ask myself, how would I implement the factorial given this issue? So I can't solve factorial using Ben Eater's original instruction set on the original SAP-1 computer because there's simply not enough RAM. So the question is, what are my options? How can I potentially solve this? First option is to increase RAM. This is a pretty straightforward thing, though the project to add RAM to the SAP-1 is actually fairly complex, but conceptually this is a fairly straightforward solution. Needs more RAM? Add more RAM. However, I didn't want to solve it that way. The reason I didn't want to solve it that way is because I wanted to make sure I understood how the various registers and the various parts of the computers interact with each other. So I wanted to kind of challenge myself to solve it in a different direction. So that wasn't an option. The second option that I considered was to add more registers. If you look at the original Python code and even the SAP-1 code, to implement this, you'll see a lot of code was dedicated to managing the I and J variable. Basically, those loop variables that control both the accumulation of the results and the actual multiplication loop each time that you have to do it. A lot of that code goes to managing that, and if you could instead move those variables into registers, that would remove a lot of that code and also not require the memory space that was dedicated just to maintain that register value. However, you would still, in the current instruction set, you would still need to move the value in that register into the register A just to do the operation of adding one or subtracting one, basically to go through that loop. So that in itself is not an option either. The third option is to add registers that can increment or decrement the value that's in the register itself. The reason why this would be useful is because then you can remove all the code that has us moving the loop variables, the I and J variables, in and out of the ALU in order just to subtract one or add one to it in order to manage that loop. So the question then becomes, is there a chip that I could use in order to do this, to affect the desired behavior? And the answer is yes. It's a 74LS169 up-down binary counter. And the aspects of this chip that make it useful for this is, first, it is a 4-bit flip-flop register, much like the flip-flop registers that we use in A and B register, and even the program counter, which itself can be increment, but it can't decrement. The second thing that's useful about this chip is that you can load the register value queued off of a clock signal. This becomes important for any kind of chip or register that you add to this breadboard computer, that it be actually queued off a clock signal. If it's not, it becomes difficult to coordinate the movement of data in and out of this chip in coordination with the other items in the SAP-1 computer. The third item that makes this chip useful is that, as desired, it can increment or decrement the register. It does this also queued off a clock signal, which again makes it easy to coordinate with other aspects of the computer. Finally, it does have a carry look-ahead circuitry, and what this allows us to do is to chain two or more of these chips together so that you can actually do larger bit operations. That is, if I use two chips rather than just the 4-bit register that one chip would allow. So what we have here is the design I came up for this counting register that I will be using in order to implement the factorial. At the core of it is the 74LS169, two of them in fact, so that I get an 8-bit register. And you will see if you look at it, the general shape of it looks very similar to the A and B register. We have these what look like flip-flops, a 74LS 245 in order to kind of moderate the output to the bus, control lines coming in. But there's a few other things going on, so I'm going to explain them. So the 74LS169, it takes input from the bus. It comes in and it has input pins, much like the other flip-flops that we use. And these input pins will read what's on the bus. When the input line, the II line, is high coming into it, but this inverter converts it to low, so it's an active low on the chip, and the clock signal goes high, and that will read it in and set the value in the register. Similarly, to output the value that what's in the register to the bus, you set the output enable line for the 74LS245. You set it low. It's coming into the module high right here in the I/O line, but the inverter converts it to low, and that will export whatever is being presented on these outputs of the register, the flip-flops, out to the bus line. So, in this works very similar in that regard to the A and B register. But the other things that are going on are these other input lines, control lines. You have what I call the I enable and the subtract line. This is the exact same subtract line that goes into the ALU. So what this I enable line does is basically it tells the 74LS169 to increment or decrement the value that's in the register. And the way these two chips are wired to each other, it does so with a cascading carry forward. If the increment exceeds the 4 bits that this register can hold, it will then increment the value there. Now, when this subtract line is high, which then gets inverted to low, this will tell the chips that when the IE signal goes high and inverted to low, that it should subtract or decrement rather than increment. So the way you control the increments and decrements is that signaling the control signal of IE or I enable alone, that will increment the register, and signaling I enable with subtract high, that will decrement the register. So that's how that works. Now, one of the things I wanted to be able to do is capture the flags, and that is the 0 flag and the carry flag, much like you do in AOL. The 0 flag would tell me when the value has been decremented all the way down to 0, and the carry flag would tell me when the value has been incremented beyond the point what 8 bits can actually represent. So detecting 0 is done similar to the ALU. You have these NOR gates that then feed into an AND gate, and when this value is high, that means the value that's contained the output here is 0. So that's fairly straightforward. Detecting the carry is a little bit more complicated. The carry look-ahead circuitry that the 74LS69 already has isn't really a signal that the carry flag, it's not really a carry flag in the traditional sense of word. What it's doing is actually setting up the next higher register, telling it the next time that I enable actually fires that it should then also increment. And so really what it's saying is that what happens is this carry flag activates when this register is actually all ones, or so 111, so that it knows that the next increment that it gets would basically carry out of here. So it activates this register so that when this I enable fires, this increments and it rolls over to 0 because it can't hold more than 1111. But then this also increments from whatever value it had. So in that way, it captures the carry forward. But this carry forward line being activated doesn't necessarily mean that the carry flag should be set. And so I have to detect that case. And you got to determine what is the scenario in which the carry forward flag would be fired in the same sense that it's fired in AOU. And that ends up being a logical condition. And what the logical condition is that the entire register is actually 0. And the I enable flag is high, and the subtract flag is low. So why that means that the carry flag should be assigned, imagine if all of these outputs were set to 1. And let's imagine that scenario. They're all set to 1. And you trigger an increment. What's going to happen is all these values will then become 0, right? Just because it's going to roll over, and because it can't hold the 9-bit value of 100000000. And so that's the case that we want to detect. Now, if these were 0 and the I enable is not activated, doesn't mean the carry flag was set. So it's all the conditions together. So when this is activated and this rolls over, so this both being true, that as these are all 0s and I enable is high, it would be an indication that the carry flag possibly should be set. but it's not complete because you got to imagine the other scenario where what if these were originally 0000001 and the IEnable was activated with the subtract flag, the subtract signal being high. That would mean that we got to 0 by subtracting 1 from, or decrementing from 1, and we want to make sure that's not the case. And so that's why we check to make sure that the subtract flag is actually low and thus not high and all that. To detect that, I use this 74LS21, which is an AND chip that takes 4 inputs. I only needed 3, so you see that one of the inputs here I actually just tie high straight away. But what I'm looking for is that the 0 line, which is this one here, is high, meaning the contents is 0. That the IEnable is high, meaning that I've just activated the increment, and thus this line is high, and that subtract is low. But since this subtract is going through an inverter, really I'm looking for the output of this inverter to be high. And so when all 3 of these items here are high, that means the carry flag should be set. Now, the problem here is if you think about it, this value, let's just say we're in a situation that is going to be high. This value is only going to be 1. It's only going to be 1 somewhere after the rising edge of the clock, because at the rising edge of the clock, that's when this IEnable is actually acted on within this within the 74LS69s, right? And so if we try to read this carry flag at the rising edge of the clock, the increment actually hasn't occurred yet, and so the values won't exist. And so if I wait, but if I do read it at the rising end of the clock after the increment occurred, which is basically the next clock cycle, it's not really the carry flag anymore. It's the next operation. All the values would be 0. In reality, I'm incrementing it to 1. And so that operation is not the carry flag I'm looking for. So we end up having to read this at the end of the clock cycle. So rather than reading the status of this at the top of the at the rising edge of the clock cycle, I'm going to read it at the trailing edge of the clock cycle. And so I need basically a cache in order to save the value of this, so that at the next clock cycle we can actually act on it. And that's what I use this 74LS173 for. You'll notice that this 74LS173 is clocked by the inverted clock signal, and so that means it's only going to read in values at the trailing edge of a clock. And so what is going to happen is when the clock signal goes high, the chips will increment, and then we'll get in the state where these values are all 0, setting this flag, the IEnable is high, and the subtract is low, which in turn will be high through this inverter, causing this carry flag to be high. And then at the end of the clock signal, that's when I clock it into the 74LS173. So that means these flags are only captured at the end of the clock cycle, and thus cannot be acted on until the next clock cycle for the rest of the computer. In reality, this ends up being similar in some ways to how the ALU actually works, because if you pay attention to microcode, you actually don't act on the flags of a addition operation until the clock cycle after that addition operation. So this will affect the same thing. But you need that cache just to kind of save that state long enough until the next clock cycle. You notice all these enables and everything that controls this chip are kind of tied low. So this is in a permanent mode of just capturing whatever's at the end of the clock cycle and maintaining it until the end of the next clock cycle. But that works. And then this then feeds into the flags register for the flag register to capture it for a more longer term, so that the microcode can act on it. So this ends up being how the register is designed. And I mentioned how the flags register needs to read into this. So let's look at the original flags register that Ben Eater designed. And so the original flags register in his design is right here. This is everything that it had. It's another 74LS173 that's controlled by this flags in flag. When this flagged in flag is low and the clock signal goes high, then it'll read what's on either of these flags lines, this one being the 0 line and this one being the carry flag line, and then maintain that in the 74LS173 until it's read by the microcode for some later operation. The challenge that I'm going to have in using this flags register in conjunction with these counting registers that I designed is that I want to use the same, semantically, the same carry flag and zero flag. I don't want to have 3 carry flags and 3 zero flags. I want to use the same one. And so this input side is now going to have 3 different inputs going into it. One for the original ALU, and then one each for each of the 2 counting registers I'm going to be implementing. And so that is going to require some logic, because if I just tie these all together directly into there, there's no telling. I mean, other than an electrical issue, if one was high and the other one was low, you have a short circuit. So let's tie them together with an OR. The issue there is your system, your microcode, actually doesn't know which source of the zero flag, as an example, is actually the one that triggered it. Let's just say you just did an decrement operation on an I register, but whatever was in the ALU is also resulting in a 0. And if you test for 0 and you don't know which one is sending the 0, you kind of have a problem. So we have to change the the flags register design also in order to account for that. So the change to the flag register design that I came up with looks a little bit like this. And what you see here is I now have 3 flags in commands. This is the original ALU one. You'll notice I changed it from Ben Eater's original FI to some flags, to indicate the ALU. And then I have the I register flags and the J register flags. So these are the control lines that are used to tell the system that which flags register I want to read from. And then I have the actual flag values coming from each of the registers. Here's all the 0 flags from the ALU, the I register, and the J register, and then the carry flags from the ALU, I register, and the J register. So what the logic here is going on is basically when any of these flags in control lines are high, we're going to want to read in whatever is on any of these flag registers into the flag register that then the control logic will use later. And so I OR these together, invert it because this is an active low chip for this control line, and that's how that's what signals to this 74LS173 to read the actual flag line to determine how to set itself. Now, the thing is, going back to what I mentioned earlier, is we need to control which source of the flag signal to be used at any given time. I then also have to take these control lines that control which flag register or flag lines that we were reading in from, and then AND them with each of their respective sources so that only the one that's high ends up getting fed into the flag register for it to kind of read into its flip-flop state. So that's what all these ANDs are doing here. It's just ANDing the sources. So when one of them is high, that's the one that gets propagated forward to this OR gate. Now you'll notice this OR gate is a 3-input OR gate. It's a 74 HCT 4075. Really convenient chip. Rather than having multiple OR gates that I would have to OR 2 at a time, given the other chips that you have available, this just makes it a little bit easier. One of the issues you might notice right away is this is not LS, it's actually HCT. HCT chips are compatible with LS chips, so we're good to go there. So that's what the logic, what's going on here. And you got the normal clock and the normal clear signal. Both of these AND chips, I have used 2 AND chips, and there's 2 extra logical ports on each of them. And putting this all together is what actually makes the flag register work in the new design. That does require a small update to the ALU design. This doesn't actually change anything with ALU, except recognizing that Ben Eater's original flag register, I just took it out of the ALU design, and since I have a separate design for the flags register now. Here is actually 2 of these counting registers built. Now remember, my goal for running Factorial required that I have 2 of these counting registers. Given that, there are opportunities to reduce chip count. One of the counting registers using only half of the available flip-flops in the 74LS173. And you can see that in the design here. You see the input to the flip-flops, only 2 of them are used, the other 2 are tied to ground. And so this was a design for exactly one of the counting registers. Given that, if you have 2 counting registers, they could share the same 74LS173 and thus not have to have 2, because one of the counting registers would go into the lower 2 bits of the 74LS173, the other one would go into the higher 2 bits, and you just have to keep track of that when you implement it. The other opportunity is that you'll notice that this 74LS21, we only use one of the gates that is implemented in that chip. This chip actually has 2 gates, and so if you're implementing 2 of these registers, they can share the same chip, and one just uses one side, the other uses the other side. So I laid out these 2 registers taking into that account. You see the 74LS173 right here, and the 74LS21 right here, and they end up getting shared by both sides. Now, one of the things you can take advantage of is that, given that these 2 chips are shared, and that both registers needs a bunch of hex inverters, that you can actually lay these out in the middle between the 2. And then what ends up happening is that the 2 registers become effectively mirror images across this center control line. Now, it's not exactly mirror images, but for the most part, you can do that. By doing that, you can kind of minimize the wiring that's needed to these various control chips. Now, to make that work, you're going to have to flip these 74LS169s around so that here they face the normal direction with the notch going to the left, and here I have them facing to the right. The reason why I do that is so that all their various control pins, which are on this side of the chip, are facing inwards, and thus the wiring to these various inputs, the hex inverters or the LS173, ends up being minimal. It just makes it easier. And then that requires, in turn, that the 74LS245, the buffer here, that one of them you're going to have to wire such that it's taking its input from one side of the chip, and the other one wires it such that it takes its input from the other side of the chip, so that you'll see this mirror image as a result. You'll also notice off to the side here that I have this 74HET 125 line buffer. That's not in the schematics of my design. What a line buffer does is it takes a signal and just basically repowers it. It repeats it, but with the power coming from its own chip power. The reason why I put this in for the clock signal, and so basically what I'm doing is buffering the clock signal coming in here. The reason why I did that is at this point in my implementation of the computer, this clock signal has already been fed to a number of various other modules, and I just wanted to make sure that the clock signal coming into this module is at a good level. And so that's what you use a buffer for, to actually, if you will, kind of reinvigorate the power that goes into that signal. There will be a small little gate delay, but this computer doesn't operate at a speed where that gate delay is going to have much of an effect. So that's what this is for. Not in the design specifically, but I just decided to add it. So given all that, here's a view of these 2 registers where I've annotated what each chip is, so you can see how I laid it out. The wiring between them is according to the schematic, except of course for this line buffer here. And so hopefully this helps you, if you're going to build this, helps you kind of build it similarly. One thing I'd like to point out is that, notice on my computer I always use these LED bar graphs rather than using discrete LEDs. I like using that because it just feels cleaner and it's easier to kind of set up. There's a few locations where I do have to use discrete LEDs, but in general, if I can use a bar graph, I do. Alongside of them, you'll see these resistor arrays that I use for my current limiting resistors. You should always use current limiting resistors, not only to limit the current, but also maintains the correct voltages across signal lines. I like using these resistor arrays because they are just cleaner, and it just keeps the design less cluttered as a result. Okay, let's pull this all together. Here you see my microcode design. You saw this in my prior video where I discussed the expansion of the control lines, and so this is kind of a diagram I use to kind of lay out what control line is controlling what, and then what are the resulting instructions that I enable with the computer to be able to get things done. And so this is an updated schematic that shows how these new counting registers will be used to help me to create commands or instructions that will be used to implement the factorial. One of the first things to note is the new control lines that I had to enable. First of all, I had to create the I enable and J enable, which are in positions 8 and 9. What these do is tell the I register and the J register to increment or decrement if the subtract flag is also high. I also had to create the lines for the I flags and J flags, that is, read in the I flag and J flag in positions 15 and 16. What these do is tell the flags register basically which source of flags to use, and it's used in conjunction with the sum flag, which is right next to it in position 14. Also implemented is the I register in and the J register in on positions 22 and 23. These are synonymous to the A register in and B register in, which is used to kind of read the value from the bus into the register. And conversely, also have I register out and J register out in positions 34 and 35. These are again similar to the A register out and B register out that we implemented previously. These positions that I used for these control lines were open control lines on the control line expansion that I talked about in my last video. These position numbers are left to right according to the status LEDs that I implemented in that design. And so with position 1 being the leftmost LED and position 36 here being the rightmost LED. This is how I keep things straight. This is how things were wired in the original design. The assignment of what control lines go to what position, that's always arbitrary, and this is just the layout that I ultimately used. As I discussed in the last video, I like to keep all the in registers and the out register control lines together, because none of them are going to be actually activated at the same time. That is, no ins. There won't be two ins at the same time, and there won't be two outs at the same time. So putting them on this HET to 238 kind of makes sense. Also, we'll point out that the subtract control line here is also used by the A and J register. This is the exact same subtract control line that is fed into the ALU to control when the ALU actually does subtract. So technically, when I activate a decrement on an I and J register, whatever is in the A and B register are going to get subtracted from each other also. But that's okay, because if that happens, as long as we don't do activate the sum out line, nothing will change on the bus or in any of the registers. I also want to highlight that I renamed the load immediate A instruction that Ben Eater originally implemented to set value A. The reason why I did that is an instruction that I want to implement is the load I register, and the LDI mnemonic just seemed make more sense with the load I rather than the load immediate. So renaming load immediate to set A, still the same thing, just a different mnemonic to kind of keep things straight. And so now let's look at the new instructions that we were implementing so that we can calculate this factorial. The first one is what I just mentioned, the load I. What this does is load a value into register A from the memory address found in the lower 4 bits of the instruction. This is exactly the same as how the load A instruction works. It's just this time it loads into the I register rather than the A register. Then I implemented this move A to I command. What this does is copies the value in register A into register I. Whatever is in A kind of is also in the register I at the end of this command or instruction. Similarly, I made a move I to J, which copies the value in register I into register J. You'll see later how these get used in the actual program. Finally, I implemented a decrement I and a decrement J, and respectively what they do is signal the I and J register to decrement whatever value is in the register at that time, and then set the flags register as appropriate. Now let's look at the actual microcode for each of these commands. The load I looks very much like the load A, except that register in actually occurs on the I register rather than the A register. So that one, we're all familiar with. The move A to I ends up being a pretty simple command. To activate move A to I, all you need to do is set the A register to output and the I register to input, and that's all that happens in this instruction. Similarly, the move I to J, same thing. Set the I register to output and the J register to input, and that kind of copies the value over. The decrement I is a little bit more complicated. What we are doing here is we have to set the subtract flag and the I enable in order to set the control lines correctly to tell the 74LS169s to actually decrement the value rather than increment. And so that is the first step in this instruction. And then the second step is to tell the flags register to read in the flag state from the I register. And that's what this IF instruction or control line does, as you recall from our discussion about the flags register. The reason why it happens on the next step is remember that the flags cache that we implemented within the I and J register itself it reads the flag state on the trailing edge of the clock cycle. So even though this increment occurs on the prior microcode step, the flag state or the flags cache is not set until the end of that step is done. That is when the trailing edge of the clock signal for that step. And so it's the next step on which the flags register needs to read that cache in order to understand what the flag state is, and thus save it into the flags register for usage for whatever conditional jump you want to do later. Similarly, the decrement J register similarly laid out, except we're decrementing or enabling the J register in the first step and reading the flags from the J register in the second step. Similar to the control lines video, I wrote a Python program that would generate a binary image to burn into the EPROMs. In fact, everything is very similar to that program, and so I'm not going to go over the details of how that program works in this video because I did it in the prior video. However, there were some modifications in order to implement these new control lines and these new instructions. And if you like to look at that code, it's available in my GitHub repository, which I will link in the description of this video. Now let's look at the code that would be used that would use these instructions that we just implemented in order to calculate factorial. First thing to note is that this all fits within 16 bytes of RAM. So that goal that I mentioned that I wanted to do this in the original 16-byte RAM footprint that the SAP-1 has, accomplished. So check. As you look at this and you kind of look at the way this code is laid out, one of the things you probably will note is that this code is very similarly structured to the Python code that I showed at the beginning of this video. That is, there are two loops, one controlled by the I register, one controlled by the J register. The A register plays the part of the results variable that you saw in the Python code, and that is the variable into which the results are accumulated into. And then there's a memory location, specifically the memory location 14, which plays a part of the X variable that you saw in the Python code. And this is used to affect the multiplication loop that the J register is actually controlling, which is the inner loop that you saw in the Python code. So let's see this work. Now that we've gotten this all together and we understand the program that we need to write, let's go ahead and do it. First thing I need to do is actually burn these EPROMs with the new microcode that, again, you can download it from my GitHub repository. So let's take it off the power and start burning these EPROMs. Okay, there we go. EPROMs are all burned. Now let's power this on and start programming the Factorial program. Of course, it comes up in a random state, so let's reset that and go into programming mode. And so I have conveniently actually already kind of figured out what the machine code I need to implement for each of these steps, and so that's what I'm about to do. And memory location 15 is actually the end value that we want to calculate the factorial against. So I think the first time we run this, we'll go for calculating the factorial of 4. So let's set it to 4. And there we go. That, I believe, should be everything in order to calculate factorial. Now that we got that programmed in and we have 4 in the memory address 15, let's go ahead and run this and see how it runs. I've changed kind of perspective here that you can see it, so you can see all the interesting parts happening on the computer at the same time, most notably what's happening in the I and J register in conjunction with what's happening up here in the ALU. So let's see what happens. Turn it on, and it's off and calculating. You can see the I and J register kind of counting down, each in their for their own loop, with the J register, remember, being the inner loop, so it's moving repeatedly while the I register moves slowly. And factorial 4 is 24. Make sure that's not a fluke. Let's go ahead and go back into program mode. And let's, instead of calculating a factorial of 4, let's calculate the factorial of 5. Program 5 in, reset the computer, and go back into run mode. Again, I like watching these two. You can tell this is an inner loop, but given the fact that it repeatedly cycles through, and the outer loop is slowly counting down. And then you can watch the ALU up here accumulating, especially the A register accumulating the value. And the factorial of 5 is 120. So there you have it. We have a working factorial implementation using counting registers and the rest of the SAP-1. So one of the things I want to point out is that managing loops is not the only application for these counting registers. Other uses could replace the program counter, though decrementing is not needed for the program counter, but the same chip could be used in a pinch if you don't have access to what was originally used in the program counter. It is ideally suited for a stack pointer, which needs to be both increment and decrement the value that you store in the stack pointer register. If you're unfamiliar with what a stack pointer is, I may be exploring that later. But the quick story is stack pointer is used to store some information, or it basically store information in a queue kind of manner, and the stack pointer points where the latest bit of information is, and you push stuff into this stack and you pop stuff out of the stack, and the pointer keeps track of where the top of that stack is. And so ideally one of these counting registers could do exactly that. You can change the reference by pushing some data into the stack, and then you would decrement the stack pointer to kind of move the memory location that it's pointing at, and then once you pop things out of the stack, you would increment the stack pointer to kind of reflect that this stuff is no longer in the stack. Another use case is actually the memory address register. Right now, this may seem, if you've just built the SAP-1, you may not see the role of this in a memory address register. But when you get into larger address spaces and you start doing more complex instructions, especially instructions that operate on multiple bytes at a time, it actually becomes pretty convenient if you could increment the address in the address register without having to put it through an ALU just to add 1. So having a counting register as the memory address register allows you to very quickly kind of scan through memory addresses that are in consecutive blobs. So another use case that I may be exploring in the future. So thanks for watching. Hope you enjoyed this video. Hope you found it educational. I know working through this project was educational for myself, and I just wanted to share those insights with whoever would be interested in them. If you do like the video, do give us a thumbs up. I hope to make a few more videos on a few other projects I have in mind, some of which I've mentioned in here. I do want to expand the RAM on this board. I do want to enable 16-bit math in the hardware and maybe 32-bit math in the software. These videos, admittedly, will be slow coming, so I apologize up front if you're eager to get more. I do this on the side, if I could say it that way. So it's not, making YouTube videos is not my focus. But be sure to subscribe to my channel if you want to get notification when I do come up with the next video on the Ben Eater SAP-1 expansions that I've been working on. Until then, goodbye, and thanks for watching.